Hey everybody, let's look at this one from 2011 here, a little buoyancy problem one. And so it says that we've got a beaker weighing 2 newtons, filled with 5 times 10 to the negative third cubic meters of water. A rubber ball weighing 3 newtons is held entirely underwater by a massless string attached to the bottom of the beaker. The tension in the string is 4 newtons. The water fills the beaker to a depth of 0.2 meters. We can see that there. And water, just in case you forget, has a density of 1,000 kilograms per cubic meter. The effects of the atmospheric pressure may be neglected. Okay, that makes things a little bit easier. So let's get to the very first question here, which says calculate the weight of the entire apparatus. So we're going to sum up all the forces of gravity. We got the force of gravity of the ball plus the force of gravity, here I'll put a little G there, force of gravity on the ball, force of gravity on the, beaker, I'll call it container so I don't get it confused with ball, and there's the force of gravity on the water. We've got all of those things there. 2 of those they told us right off the bat. They said that the beaker weighs 2 newtons and the container weighs 2 newtons and the ball, that's what that stands for, weighs 3 newtons. So we got to find the force of gravity on the water there. So let's do that. So the force of gravity on the water will be the mass of the water times gravity. And now let's do our favorite substitution of this unit. Mass of water can be replaced with density of water times volume of water times gravity. And now let's just plug in all of those. So we get 1,000 kilograms per cubic meter for the density. The volume they told us was 5 times 10 to the negative third cubic meters, and then gravity is 10 meters per second squared. And so that will work out to be, these two will cancel out and give you 5, and then times 10 will be 50. So the water itself weighs 50 newtons. So when we add up the force of gravity on the ball, which they said was 3 newtons, and they said that the container was 2 newtons, and then we add up the water itself, which is 50 newtons, that means that the sum of all the forces of gravity winds up being 55 newtons. So that's the weight of the entire container there. So below, draw a free body diagram on it. Well, we know that we've got gravity down on it, and we also know that we have a tension from the string down, and we know that we have a buoyant force up. And on this particular one, they didn't give a grid. If they did, we would know to make the buoyant force equal to the strength of these two combined, because there's no net force because the ball's not moving anywhere. Okay, so next up here, we're going to calculate the buoyant force exerted on the ball by the water. So don't add anything to your other drawing there. So let's think about this. We know that the buoyant force up minus the force of gravity down minus the tension down, that those all cancel out and come to 0 newtons because the ball isn't moving anywhere. Okay, so now let's just rearrange this. They want the buoyant force, so we can just say that the buoyant force is equal, let's move these two to the other side, the force of gravity plus the force of tension. They told us both of these on the ball. They told us that the ball weighs 3 newtons, and they told us that the tension was 4 newtons. And so add those two up, and that gives you 7 newtons must be their combined force, and therefore also the buoyant force on them. All right, calculate the pressure due to the liquid. In other words, the gauge pressure at the bottom of the beaker. That's easy enough. The gauge pressure is the density of the water times gravity times height, and we simply plug those in there. It's 1,000 again is the density of water, kilograms per cubic meter. Gravity is 10 meters per second squared. And the height, if you look back onto the picture here, was 0.2 meters. And so we can plug that in. And then 0.2 times 10 is 2, and then 2 times 1,000 is 2,000 pascals of added pressure from the liquid itself. All right, last part here. It says the string is cut and the ball rises to the surface and floats. Indicate whether the water level is higher, lower, or the same after equilibrium is reached. So in other words, if I look here, the ball is going to rise up and it's going to float somehow, something like that, let's say. And so I'm going to use that picture when I look here. The answer is going to be lower. And then there's two ways to sort of think about it. So the ball is at least partially above the water because it's floating. And that means it displaces less fluid. And so that's the easiest way to think about it there. There's another way you could sort of arrive to the same answer here. So you can think about it that according to Archimedes' principle, that the buoyant force is proportional to the volume of the fluid displaced. And we know that originally the tension was 4 newtons. And so plus the weight, so we knew the buoyant force was 7 newtons altogether, right? We already calculated that. But when it gets to the top, the buoyant force, since there's no more strain, is just going to be equal to the weight of the ball, which is 3 newtons. So since it's displacing less, since it has less buoyant force, I should say, then that means it's got less fluid that it's displaced.